This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio brings you relevant and detailed discussions and interviews on software engineering topics every 2 weeks. Thanks to our audience and the partners listed on our website for supporting the podcast.
Okay, so welcome listeners to another episode on Software Engineering Radio. This time we have invited Doug Simon from Sun Labs to talk about some Java virtual machine implementation project called Maxine. Welcome, Doug.
Thank you very much.
Doug, would you introduce yourself to our listeners?
So I'm Doug Simon, as mentioned, and I work here at Sun Microsystems Labs in California, the Menlo Park campus, and I've been a staff member here since 2001, but I actually was here early in 98 as an intern and worked on a project called Spotless VM, which morphed into something called the KVM and became the reference implementation for the CLDC specification when it went out, I think in 2000. And prior to that, I completed a CS degree at the University of Queensland in Brisbane, Australia, under Christina Cifuentes, where I worked, or my final thesis, honours thesis, was in the area of decompilation, where I was looking at mechanisms for recovering C-like control constructs from assembly code. But since being back here in 2001, my focus has been almost solely on JVMs.
And you're now working on another JVM called Maxine. Can you tell us a bit more what is Maxine? What is it about?
Okay, so the origins of this project can probably be traced back to the mid-90s, where a couple of researchers at Sun Labs by the name of David Unger and Mario Wolczko were interested in researching hardware support for objects in the context of a managed runtime, in particular in the context of a VM. So what they were interested in is looking at object references which aren't necessarily addresses to a flat piece of memory, but indexes into some hardware-based object table. And they thought, well, to conduct an experiment, let's use an existing VM and modify what exactly it means to reference and dereference objects. And in surveying the landscape, they found such an experiment may not be so easy to conduct, given that there's, this concept of what an object is and how you dereference it is traditionally spread across most parts of a VM implementation, or significant parts, and to conduct the experiment, they'd need to understand vast quantities of any VM. So they got to thinking about how one could design a VM where this subsystem of looking at objects or handling objects is sort of as contained as possible and disentangled from as much of the rest of the VM as possible. So the sort of realization they had is one of the core architectural concepts of Maxine, and they sort of decided that if you can build a VM around an optimizing compiler where the knowledge of any subsystem is bootstrapped into the compiler, then you get this disentanglement for free. And hopefully in later parts of the interview it'll become clear what I mean by this bootstrapped optimizing compiler. And so that's where the idea sat for a while, around, I'm not sure what date it was, I think 2003 or 4, Bant Matiska came back to the labs after being in product land at Sun, where he was the tech lead on what's called the CLDC HI, the CLDC HotSpot implementation VM. So that's in the same space as the KVM, but a more optimized implementation of these small VMs. And he was interested in sort of taking ideas he'd learned from that and previous projects and scaling them up into a new type of full J2SE VM, and he shared a lot of the ideas Mario and Dave had, and thus began the Maxine project. And that was around 2005. I joined in 2006, and we've had subsequent team members join since then: Laurent Denez, Michael van der Vante, and Ben Titzer. We also had someone else working as an early contributor, Greg Wright. So the VM itself is written in Java. We use the latest Java language syntax as of Java 1.5. In particular, we've made heavy use of annotations to sort of basically to write a VM, a Java VM in Java, you have to, depending on your point of view, extend or break the language. But, to write a garbage collector, we need to be able to talk about such things as pointers, which obviously you can't natively do in Java. So through sort of a combination of annotations and other mechanisms, we've added, basically we have a new type hierarchy, a separate type hierarchy in the language, which allows us to do these low-level operations. And then the trick is to build on top of this, what we're after is a highly modular, componentized design, so that we can do these experiments on VM subsystems without necessarily having to understand every other part of the VM. And not only us, but we'd like to, have other researchers in the VM community be able to use this artifact to conduct their research. I guess, that the core idea is build everything around an optimizing compiler. And if you'd like, I'll go into more detail on what that means.
Implementing a Java virtual machine in Java sounds a bit crazy from the first point of view.
That is a very justified, correct initial reaction, which I had as well. And this actually has a history in Sun Labs. We had a project here in 98 called Java in Java, which was exactly that, a Java VM written in Java, running on top of another Java VM. And not surprisingly, I think we found that performed on the order of 1,000 times slower than a standard Java VM. So you're right in that the naive approach definitely doesn't buy you anything, actually costs you a lot. But if you think about what a VM for any language does, or a VM at least that has a platform-independent bytecode format to machine code compiler in it, does, at runtime, it runs this compiler over a set of class files producing machine code, which is directly executed on the hardware. So if you can sort of push that understanding one step further and say, well, what if we actually not just put that machine code into the runtime memory and executed that, but saved it to a file? And so in some sense, you can deploy or execute your compiler in this manner in what we call ahead of time compilation, running your compiler written in Java as a Java application on top of an existing VM, but saving the compiled machine code and the associated objects to a file. What you effectively have is an executable produced by your compiler that contains your compiler and the rest of the runtime system necessary to have a standalone bootstrapped VM.
Doesn't mean that you first run your own VM that is written in Java on top of another Java VM. Let the JIT compiler compile your Java VM itself somehow, and then save that's the produced machine code to a file and start from that again without a host VM?
Exactly. So we have, if you think about C compilers now, what are they written in? They're written in C. So you do need a pre-existing C compiler to actually bootstrap a C compiler. In some sense, this is no different. At some point, as with most C compilers, we'd like to bootstrap our VM with our VM. But for now, until we get the performance we need, it's expedient to use an existing VM, HotSpot being the obvious and natural candidate. So it's in some sense not too different from the way you bootstrap any other compiler-based system. It's just that typically this is not how Java VMs have been built.
Why did you choose Java as a language?
So we wanted to build a Java VM. Now, why did we choose, Java as the implementation language as well as the target language? Well, this is not the first VM to take this approach and realize some of the benefits of doing this. In the Java space, we have the JIX RVM, employs a similar technique, as does the Squeak VM, the Smalltalk VM, written in a subset of Smalltalk. In addition, we have another project here, which I was part of, called Squawk, which is a CLDC class VM, itself also written in Java. But by implementing it in Java itself, you get a lot of the nice features of the Java language, which one could argue, make it a more productive implementation choice than something like C or C++. For example, in our class loader, the VM's class loader, we can write this in Java using exceptions when things go wrong. We don't have to pass all sorts of macros around to recover in a safe manner. Actually, and even more importantly, we get garbage collection for free. There's large parts of a VM that use dynamic memory that aren't, part of the GC implementation itself. And if you ever look at the HotSpot source code, every time a Java object finds itself down in the C++ source code, they have to have a separate mechanism to let the garbage collector know about the C code holding onto or having a reference to these objects. It's something they call handles, which adds a level of inefficiency in handling these objects. And also it can be a nasty source, a source of nasty bugs if you forget to use handles in the right place. We don't have to worry about forgetting because the language we are compiling and writing the VM itself is garbage collected. There's other benefits such as diminishing the barrier between the application code and the VM. Every time the application makes a call into some VM subsystem, if you cross this language barrier from Java to C, you need to perform extra work. Your layout of frames may be different depending how you write your Java compiler. It may well differ to the frame layout used by the C compiler. And so you need to shuffle things around. You need to effectively marshal things potentially into different locations every time you cross that barrier, not to mention having to wrap objects in handles. So there's that sort of overhead of going through the barrier, execution overhead, but there's also a barrier to optimization. We can actually inline parts of the VM into application code and obtain all the well-known benefits of inlining. And this has actually been taken one step further by another project here, which is built on and using the Maxine VM called Guest VM, run by Mick Jordan, where he is putting Maxine directly on top of Zen, where he's now at the point of rewriting the thread scheduler. So he can effectively make optimization decisions that are boiled down and aware of the thread scheduling logic straight from the application code. You can also optimize all the way down through the network stack. So you get this sort of diminishing barrier to both execution overhead and optimizability. So these are just some of the benefits of doing it in Java. And then there's great tool support for Java that works pretty much the same on all platforms. Even though our primary target or initial target for this VM is a AMD 64 system, the members of the team can quite happily develop, compile, and debug most of the VM using a standard Java IDE on our platforms of choice. Currently, we all develop at various times on a MacBook, on a Solaris system, on a Linux system, etc. And then we also get the portability aspect. It's just, in general, the portability Java brings to applications, we get a large part of for the VM. Other parts, such as adaptive optimization, can be applied to the VM itself at runtime, so the VM can sort of trace its own execution and start rearranging or inlining its code differently.
So all those optimizations that we know that HotSpot
yes.
does?
That's the ultimate goal, is to apply all well-known VM optimizations to not just the application code. HotSpot cannot dynamically optimize itself once the VM has been deployed. They didn't write and they don't control the C++ compiler, and it's sort of fixed in stone once the thing is out there and running. That being said, to realize this ultimate goal of optimizing all over the place, we actually need to implement those optimizations. And given that the optimizations determine the quality of the VM, we have the sort of dog food principle here. Once your dog food's of a reasonable quality, it can only get better and exponentially so. But until you're at that point, you actually have something that can be quite substandard compared to an existing VM built around a compiler that's 30 or 40 years old and quite mature. So that's sort of the trade-off one buys into with this approach.
So Maxine is called a meta-circular VM. What does this meta-circular exactly mean?
So I think it's hard to nail down this definition, and so we've chosen put a stake in the ground and said, in the context of this project, we basically mean a VM that's implemented in the language it hosts and tries to express as much of the VM semantics in that language without having to hand code assembly or weave compiler IR. And I think to a large extent we've realized that goal. So maybe it's a good point for me to describe one of the core aspects of the Maxine architecture, something we call snippets. At the most coarse level, snippets are pure Java methods that they just look like and compile like and come up like any other Java method in an IDE. And what they actually implement are parts of JVM bytecode semantics. So we have a snippet, for example, called getField. And this is a bit of Java code that has a parameter, which is an object, an untyped object. And let's see what else. And a constant pool index, which is pretty much what you get from the JVM. If you look at the JVM specification, the semantics of a getField is you take a receiver off the stack, which is our object, and encoded in the instruction is a reference to the constant pool, which allows you to resolve exactly which field of the object to retrieve. So we have this Java code that simply operates on this object and this field and asks the field, it calls a method on the field which gets an offset, converts the object to a pointer, which I will go into more detail, involves many layers of abstraction. And at some point, this will boil down to machine code, which dereferences a machine address and returns the value of the field. Now, this snippet itself is now a part of the compiler. And this is where it gets a bit tricky to understand and also to explain. An immediate observation is, well, what if this bit of Java code itself references another field? Don't you have a sort of infinite recursion problem here? And it's for this reason we have a two-phase mechanism for bootstrapping our compiler, where all of these snippets are sort of translated to this unoptimized form of an IR, which calls out or references other pieces of IR. And we need to build these unoptimized forms of compiler representation for all of the snippets. And and sort of put them on a table on the side and then recompile them, pulling bits of that table, pulling the cross-reference semantics out of this table and running our optimizations over them. And to cut a long and confusing story short, what you end up with is these little bits of bytecode semantics in a table, or that the compiled and optimized IR for these bits of semantics indexed in a table, which you then use to compile any other Java code. So every time you see a get field, you say, okay, I need this snippet. So I go to this table, pull out this IR, and weave it into the IR I'm building for the method being compiled. So all the compiler really knows how to do is how to apply standard optimizations to reduce these snippets, but the actual semantics of what any bytecode does is expressed in this Java code. And this is sort of the core of what we believe could potentially give any sort of VM researchers a great deal of flexibility when you want to modify the semantics of or experiment with different ways of implementing certain bytecode semantics or bytecode implementations. Let's see what's a good example. So if we think back to one of the motivating examples for this whole project, hardware support for objects, we want to abstract away what the notion of an object reference is. And so we've encapsulated these sort of abstractions in something we call schemes, and we have this scheme called reference scheme. And a reference scheme has operations like, given this reference, give me a byte at this sort of abstract offset, or this you want to read something out of this reference. You want to dereference this reference to pull some data out. And so what exactly that entails can be tailored for different reference scheme implementations. And a clarifying example maybe references are just database indexes. Every object is really just in a database, and all an object reference is a database key as opposed to a memory address. And so you could quite easily implement this different choice of how you store objects by only providing a different concrete implementation of this reference scheme interface. And when I say interface, I really do mean a Java interface. And so the immediate observation here as well, all of these layers of abstraction perform, they provide not only a performance overhead, but surely you're going to get into the same bootstrapping problems again, trying to use references in methods which, the implementation of the reference scheme itself will invariably use references. So how do you reduce this down to flat code? And the mechanism we have is we employ a couple of very crucial annotations when writing these scheme implementations, and we call them @fold and @inline. And by @ I just mean the @ symbol used to write annotations in Java. So we can configure the VM as we build the VM. We provide a concrete implementation, or we bind all of the schemes in the VM to a concrete choice for each of those schemes, which is hanging off this globally accessible VM configuration object. And so when you want to do something through a scheme, you effectively sort of ask the configuration object, give me the reference scheme object. And this is just a method call, but by putting @fold on that method call, the request for the VM object, we say, instead of compiling this call, go and execute it right now. Sort of meta evaluation is the common term for compile time evaluation. And so the compiler now has a concrete object in its IR through which it can, which is the concrete scheme implementation. And then the methods on that scheme implementation are either meta-evaluated further or inlined. And so you don't actually have calls to calls to calls to calls. They're all inlined through. It's almost akin to macro-style inlining. This is not heuristic inlining. And at the end of the day, for something like a dereference of a reference, object reference, this all meta-evaluates away and compiles down to, your standard 3 or 4 machine code instruction sequence for pulling an object out of memory at an offset from a given memory address, assuming you're choosing to represent your objects in a standard memory, flat memory system.
Sounds like the Maxine VM is also nicely extendable by others, so by other research projects or so. So if someone would like to, would like to insert aspect-oriented programming on the VM level, would it be possible to use the Maxine project?
Our hope is that would be extremely easy, and experience we've had with collaborators so far seems to point in that direction. Recently we had Alan Gregerson here from the University of Southern Denmark, who has written a system for doing dynamic updates to Java applications based on modules, a module system. In particular, the work he's done has enabled dynamic updates of NetBeans modules where you don't have to take the system down, and the type of updates you can do. The ultimate goal is to support updates that are as powerful, reflect exactly the type of refactorings you can do to Java code. So at the moment, the HotSpot VM and other Java VMs can support dynamic updates without stopping the VM, but it's, as far as I believe, constrained to bytecode method implementation changes. You can't add methods, you can't delete methods, you can't add fields, you can't change the type hierarchy. Also, all the sorts of things you can do with refactoring. And so he's he's used the technique of bytecode rewriting or instrumentation to catch transitions across API boundaries, and sort of inserted proxies at those boundaries such that if you put a new module into the system, all existing modules in the runtime that bind to that module will now go through this proxy object, which will determine where to route certain method calls or field accesses. And so they've gotten a long way with this work, but they were quite interested in using Maxine to solve some of the problems they ran into with a VM agnostic implementation. In particular, they cannot instrument a lot of the core JDK classes without potentially breaking the VM. I don't think you can even instrument these classes at runtime. The classes in rt.jar sort of come into being before any class loaders written by external, developed or deployed by external developers get a chance to instrument them. Not only that, but there were certain transitions he can't catch at all. And one example was field accesses from native code called through JNI, which have a handle onto an object and call back through JNI to dereference that object. To effectively do this, you have to go and change the VM implementation of what's called the JNI function interface, the way you do upcalls from native code back into the VM. That, in our VM, is just one class with about, I think it's 250 methods, which is the JNI function interface, and it's all standard Java code. So it's absolutely trivial to go and do the intercept in this implementation. We've also had discussions with Michael Haupt from the Hasse-Plattner Institute in Germany, who's interested in doing something like adding something close to prototype-based support to Java. So he wants to put proxy, wants to make every object actually two objects. So the delegating object and then one or more delegatees to which method invocations or field accesses or other state accesses go through. And this gives you the ability to do, rewire the virtual dispatch of any method at runtime, much like you get with prototype-based languages. And, our initial considerations of what you'd need to do that show that you only have to touch a few parts of Maxine VM to get a long way. Of course, until the experiment is complete, we can't be too sure that we've gotten all the abstractions correct. And we have a number of other collaborations with people sort of building on top of Maxine to do things like software transactional memory. That's a group in Sun Labs, in particular Virendra and Marathe is working on that. We have a collaboration with the University of California, Irvine. That's Michael Francis' group, particular Andreas Gall, Michael Bebenida, and Kartik Vanavan, implementing a trace-based compiler in Maxine. This is the same compilation techniques used in, I think it's called TraceMonkey, one of the JavaScript optimizing compilers in Firefox or about to come in Firefox. So, current experience shows, the VM is penetrable and allows for certain sorts of experiments to be conducted fairly easily.
You said that the Maxine VM it's written in Java, so it's different than HotSpot and can optimize itself. So how does it relate to the what you already mentioned, the Maxine Research VM?
So I'd say the core defining difference is this architecture we have of building everything on top of the compiler, the optimizing compiler, and expressing sort of the VM semantics in Java code, which are bootstrapped to become the translation units of the compiler. If you look at HotSpot, the both compilers, of which I think there are at least two, are sort of hand-coded monolithic implementations. Whereas in Maxine, currently we have this optimizing compiler around which we build or derive a JIT compiler. So the optimizing compiler is actually relatively slow to execute, even though it produces, at this point, okay machine code. But it's unbearably slow if this was the only execution engine you had in the VM. So what we built is a very fast template-based JIT compiler. And the way to explain this is if you think about what we do is we write Java methods that almost look like you're writing an interpreter in Java. And we compile these methods, and each method is a one-to-one correspondence with a JVM bytecode. And all it does is express the semantics of that bytecode in Java code. We compile that method with the optimizing compiler, cut out the resulting machine code, and put it in a table indexed by that bytecode's opcode. And so to run this compiler, it's basically a memcopy operation is the closest analogy to where we'd like it to be. You parse a sequence of bytecodes, you pick out the opcode, decode the operands, pull this bit of machine code out of the table. If necessary, patch a few values in the machine code to represent the decoded operands, and copy it to a code buffer. And the hope is, this execution engine is fast enough that we can do without an interpreter. And in that sense, we're not too different from JIX, which, by my understanding, does not have an interpreter. But I think, the core difference is this architectural decision to really build everything around this optimizing compiler, allowing for the semantics of any part of the VM to be expressed in one place. And there's other sort of minor artifact differences. We came to the game later, so we can, one thing we've tried to stay away from, we've managed so far, is any sort of source code pre-processing. You can download the Maxine source code and it'll come straight up in an IDE without having any sort of pre-configuration applied. Other differences, at least with JIX, from the get-go, we've implemented native threads. I hear recently JIX has also implemented native threads, but until that time they were end-to-end sort of green-threaded model where they did their own scheduling on top of native threads. And there's pros and cons of each, but it seems as though industrial VMs are going, industrial strength high-performance VMs have always chosen native threads, and that's, we learned from that decision and chose them from the beginning. Another interesting aspect is we have a single instruction save point mechanism. Save points in VMs are the way in which you can stop a thread for the purpose of, for example, you want to run a garbage collection. You need to be able to know the execution state. In particular, you need to know where all the references are at the execution state, in the execution state of every thread in the system. Save points are one way to achieve this, where you can make sure each thread is stopped at a point where you have some metadata saved describing where the references are. So the save point mechanism we have, we needed one that would allow us to stop not all threads. We don't want a mechanism where as soon as you trigger save points, all threads stop. And the main reason is we have a garbage collector running on, written in Java, running on one of our threads. So obviously we can't stop that thread. So we came up with a mechanism where it's per thread enabled, and it actually only takes one x86 or AMD 64 instruction to instrument the code to put in the polling, or is it called polling? The trigger for the save point. We've, given that we want to make as many parts of the VM as configurable as possible, we've put a lot of work into coming up with schemes for various parts of the system. We have schemes for how objects are laid out, what references look like, a scheme for what your garbage collector implementation choice is, and numerous other aspects of a typical VM. We feel it may be important, we're not sure. Difference is that we aim to be, and have so far achieved this goal of being, a drop-in replacement for HotSpot. So you can download the standard JDK and execute our VM on top of that. We're not dependent on GNU ClassPath or other alternatives to the standard Java class libraries, which means we can always use the latest and greatest and most complete implementation of the Java language spec. And it obviously means once our VM's stable and robust, we can run any program HotSpot can.
How is the performance compared to HotSpot?
At the moment, at best, we're about 2x slower than HotSpot, which gets us close to the threshold for acceptability in terms of conducting meaningful performance-related experiments, although one could argue you really need to be even better. We have a good plan for improving performance, which is to actually leverage a lot of or one of the compilers in HotSpot. Effectively, we're porting the client compiler from HotSpot into Maxine, with the hope to one day also using it as our ahead-of-time optimizing compiler. But there's been a lot of work, a lot of engineering years thrown at that compiler, and we've decided it's time to leverage that and also use a compiler that other people may have more familiarity with. Our current optimizing compiler is based on CPS continuation parsing style, which is or has been used in sort of implementations of Scheme VMs and Scheme compilers. But we've found through experience with interns and other collaborators, it's not as well understood as a more traditional compiler, which the client compiler in HotSpot definitely is. And it also allows us to more easily look at the possibility of transferring some of this technology back into the product VMs. We've identified some of the areas for improvement in the client compiler, and we hope to put them in, implement them as we port the compiler, and the hope is we can backport or at least suggest these improvements to the HotSpot team. So yeah, performance is not quite where we want it to be, but it's definitely enough to run a vast majority of programs and conduct interesting experiments. And the hope is those experiments results will only get more interesting without having to redo the experiments as the core compiler improves. So there's no sort of barrier to conducting experiments on the VM as it stands right now, unless you really need high performance results immediately. We hope to have this port done within the next 6 months. And we've also have ideas. The other suboptimal part of the VM right now is the garbage collector. We have a simple chainy two-space copying collector, non-generational. So while it's extremely easy to understand and it's allowed us to get up and running with a relatively bug-free collector, it's far from optimal. And we have a plan. One of the team members, Laurent Denez, is currently working with a HotSpot team to put in a variation of the G1 collector, which is currently in the OpenJDK version of HotSpot. And this is a region-based compiler. So you sort of you partition your memory space up into different regions, and you can sort of get, instead of sort of just generations, you can think of many generations, and you can get performance benefits by not having to do as much work if you sort of only create garbage in a few regions. So this implementation is currently being performed by one of our team members on the HotSpot codebase, and the hope is in the next few months he can port that also into Maxine. And after that, we really won't have too many more excuses for sub-HotSpot performance numbers. I mean, the hope is with both of those we'll be at least on par with HotSpot client compiler. So, yeah, that's the performance story today and hopefully in the short-term future.
And what about the HotSpot server compiler?
So we are not compiler experts, I'll say up front, and that is a compiler not understood by a lot of people. I mean, it's very well designed and highly optimizing compiler, but it's sort of beyond the scope of our resources to also try and port that one into Maxine. It would be interesting to have it in there, but we feel doing client is a more realistic goal and buys us, sufficient performance. I mean, in case you're not aware, up until recently, and I think it may still be the case, at least for the non-OpenJDK versions of HotSpot, every time you run, you are either running client or server compiler. And for a large class of applications, the client compiler is the default choice, or a large set of platforms, the client compiler is the default choice. And so people have been using only the client compiler for a long time and been satisfied with its performance. So it should be good enough for us in the initially anyway.
Oh, okay. Do you think that the Maxine architecture will remain a research project, or will it be the production VM of the next generation?
So this is where we can get into controversial statements, but I mean, my hope is that it's a bit of both. Primarily, we hope it becomes the primary research platform of choice. In terms of transfer into product land, we have to be honest and say we're a small team. We don't have the resources to bring it up to speed or close enough to the product performance that quickly. And our initial goal is to just try and transfer some of the technologies we've developed in the VM, some of the ideas at least, into HotSpot. So like I mentioned earlier, if our client compiler port actually makes improvements to the client compiler, we'd like to at least have the discussion with the product guys of how to put those improvements into HotSpot. A wholesale replacement of HotSpot is a very futuristic concept at this point.
Okay. I looked at the website, and there are different ports of the Maxine or different platforms available that Maxine can run on. It's Solaris and I think Mac OS.
Yeah.
So can you tell us a little bit more which platforms are available?
Okay, so at this point in time, the sort of development platform of choice that we focus on is Solaris AMD 64, just because that's sort of close to Sun's core business, and it's the hardware we could get our hands on initially. We also have a Solaris Spark port, which is lagging a little bit behind the Solaris AMD 64 port, just because of obviously differences in the Spark backend. And we actually have a new team member, Paul Caprioli, who will be hopefully addressing that over the next few months. And that's sort of particular interest to some of the other groups looking at using Maxine and Sun who want to work on especially the software transactional memory support, which would play nicely on Sun's up-and-coming ROC processor or some of Sun's highly scalable Spark processors. The hard part of any port is the backend. So given that we've got AMD 64, it wasn't too much effort to get the VM running on Linux. So we have a Linux AMD 64 port, which runs as stably as the Solaris AMD 64 port. We also have the Mac OS port completed. Obviously, you need to be running a MacBook or a Mac machine that I think has the Core 2 Duo processor, which is instruction set compatible with AMD 64. And we found actually the hardest part of these ports, apart from the Spark one, was not so much the VM itself or the compiling the VM, but the debugging support. So we have our own debugger for this VM. And one of the main reasons for that is it allows us to not be constrained by the sort of compiled frame layouts that other debuggers expect. It also allows us to leverage the fact that we know what objects look like in the VM. So our debuggers, both a sort of runtime execution debuggers as well as a object browser, much like you may be familiar with from a Smalltalk environment. And the platform-specific part of this tool has been remote controlling processes. I mean, any debugger has to be able to start a process or attach to a process and control its execution and inspect its memory. The Solaris OS has wonderful support for this. We use sort of a C interface, which is really just a C ABI or API alternative to the /proc file system on Solaris, which gives you very reliable ways to stop, start, single step, read memory from a Solaris process. In particular, what it does very well is handling a Solaris process with multiple threads, that they've very clearly separated the notion of, Solaris has a separate notion of process and threads. Darwin was also not too hard. There, the problem is your debugging interface is a mixture of ptrace and muck ABI. So there was just a little more learning to do there. But we have the Darwin debugger working almost as well as every other debugger. There is one sort of non-understood performance behavior anomaly that we haven't fixed yet. And I think the hardest challenge we had was the Linux debugger hookup. So Linux only presents you with ptrace. And ptrace closely reflects the implementation choice for threads on Linux, which is a thread is effectively a process. And using ptrace, you have an interface to a single process. So if that process, itself comprises of many threads, you have to do a whole lot of extra bookkeeping to learn about when those threads come online, when they die, and attach a new ptrace instance to each of those threads. So that was basically a couple of weeks of just staring at and trying to understand the GDB source code. But we've managed to get the port completed to the point where it's actually as easy to debug Maxine on Linux as it is on the Solaris platforms. So they are our currently implemented platforms. I'm going to preempt a question on where is the Windows port, and all I can say is yes. It's just a matter of lack of resources. All of these other platforms we've ported to are very Unix-like, and so our thin layer of C code basically had only minor differences that needed to be taken care of to make those ports work. And now that this is out there as an open source project, we'd love to work with anyone who'd like to see this work on Windows. Obviously, it'd have to be a Windows 64-bit platform running on AMD 64, but I can't imagine the overhead is too large. So yeah, that's our platform story at the moment. Actually, let me at least mention the fact that we say this VM is written purely in, or almost all in Java, implies there is some native or C code in there. And we've kept that to an absolute minimum. All our C code does, for the most part, is implement, the main entry point required of C programs, which knows where our boot image is, maps it into memory, relocates the pointers inside that boot image, and then transfers control into a well-known method entry point inside the image. And that's about it in terms of our C code. The only other thing we do with the C code is we shield some of the sort of platform-dependent ways of doing var args from our JNI function implementations. But there really isn't much else in the C code. In particular, we don't expose any heap objects to the C code. We don't have any requirement for handles in our C code. And it's so far managed to compile trivially on every C compiler we've thrown it at, so we don't use any sort of obscure constructs. Yeah, all I can say is I encourage people to go to the Maxine website, which is at research.sun.com/projects/Maxine, and at least read more documentation on what it's about. And if you're interested, download it and build it and play with it.
Great. So, Doug, thank you very much for being on the show and give us all these interesting details about the Maxine project. So thank you very much.
All right. Thank you very much, Martin. And good luck to anyone who cares to experiment with this platform. We'd love to hear back from you.
Great. Thank you.
Thanks, Martin.
Thanks for listening to Software Engineering Radio. Software Engineering Radio is an educational program brought to you by Hillside Europe. If you want more information about the podcast and all the other episodes, visit our website at se-radio.net. If you want to support us, you can donate to the SE Radio team via the website, or you can advertise for SE Radio, for example, by clicking on the Dig Reddit Delicious links and the /dot button. To contact the team, please send email to team@se-radio.net, or if it is specific to an episode, please use the comments facility on the website so other people can react to your comments. This episode of SE Radio, as well as all other episodes, are licensed under the Creative Commons 2.5 license. please see the website for details. Thanks to Charlie Crow and the Podsafe Music Network for the music used in this show. The song is called Vegas Hard Rock Shuffle.